All right. Welcome back. So we're now heading to the tokenization session. So Alex, over to you.
All right. Can everyone hear me already? Continuing on from earlier. Oh, that's fine. We're going to be still at the same GitHub repo. So if you've seen the QR code or you've been to the place before, continue there. We're now going to be going over to the training tokenizers notebook. So jump over there. Let me make this big. It's readable or all right. So without further ado, we're going to basically be going through training several different tokenizers using Hugging Face's tokenizers library on the Wikitext dataset. I know this is a scientific foundation model summer school, but it seems like it would be a really good idea to get a good understanding of what the baseline NLP, natural language processing techniques are, and to just kind of have familiarity with what's out there. We've talked so far about kind of like two relatively established fields in terms of how do we actually take that data, convert it into something that a transformer can understand, but perhaps in your particular field that hasn't happened yet, and maybe something will spark a little bit of interest. So to start off with, let's talk about what exactly is tokenization. So at a high level, the goal here is we want to be able to convert words into a sequence of integers. That's the goal. That's all that a transformer does, is it takes that sequence of integers and produces a new sequence of integers. But how do we do that? So the first thing that we're going to do is we're going to want to basically normalize our text. We don't actually typically model the actual text that is being fed into these models. We simplify it. So say you have a bunch of Unicode characters, say you have like a theta dot. Let's maybe replace that with, instead of a single symbol for theta dot, we're going to have a theta followed by the dot symbol. Think maybe we'll just lowercase all of our text to make it simple. Maybe we're going to get rid of punctuation, things of this nature. Maybe we're going to recognize that there are 25 different space characters in Unicode, and we only want to model one. That's the whole point of normalization. Now, unlike the other steps here, this is not a reversible process, but it is an important process. The next step is called pre-tokenization. This is the old school tokenization. You take your string of words, you split on spaces, and now you have a sequence of words, which are now called pre-tokens instead of tokens because things have advanced. And then following that, we're going to then take a model, which is going to take those individual words and figure out some way to convert that into a sequence of integers. So the simplest way you do this is you take an integer and you assign it to every single word and you call it a day. But increasingly, we're seeing subword modeling. So we're going to take those words and we're going to break them into pieces. We're going to assign an integer to each of those pieces. That's what we're going to model. This kind of makes some level of intuitive sense. You can think of like running is probably a run token followed by an ing token, or don't is a do followed by an int, and similar types of things in other domains. And then the last step, which is generally not used by most of the things that I think we've seen so far today, is called post-processing. And this is when you're going to add additional information or additional tokens to the sequence to account for the particulars of your task. So for example, in BERT, we're going to add a class and a separated token to delimitate the question and the answer in the input. We can also just skip this. And as we've talked, we're going to be using Hugging Face tokenizers, mostly because that's what we use. It's fast. It's got those nice Python bindings, and we like it. But there are other things, and you should check them out. Okay, so throughout the next little bit of text and throughout the rest of the examples, we're going to be tokenizing and modifying and normalizing and doing the whole 9 yards on this wonderful little poem written by ChatGPT about foundation models. By all means, change it to something more fun or interesting, or maybe throw in your own scientific data. This whole notebook, by the way, runs pretty quickly. So if you do want to follow along, you should be able to do that quite easily. All right. So we're going to start off and we're going to just do normalization. So this ends up being pretty straightforward. So we're just going to define our two operations. We're going to strip. So we're going to get rid of any leading or trailing white space. And then we're going to lowercase our text. Interestingly enough, if you were doing, say, byte pair encoding, you might actually want to add white space to the beginning of and end of your sentences, because you wouldn't want to necessarily treat, say, a good morning, where the G is capitalized because it's at the beginning of the sentence that has no leading space, from a today was a good morning, where the good morning occurs mid-sentence and has a leading space. Because byte pair encoding looks at sequences of bytes, it would see space G as different from just G and could result in a different kind of a tokenization. So sometimes these choices do have actual downstream impacts. And the recommendation here is look around, see what makes sense for your text, and also probably try a few things out. The nice thing about this stuff is it's usually, there's a pretty wide margin for sane choices before you get weird things. So as you can see, our wonderful little sentence has now become all lowercase, and there are no leading spaces. Okay, so the next thing is we have to identify what the heck is a word. And we're going to then split on that. Now, in English, it's pretty easy. Words are delimited by spaces, and we call it a day. That's not true for all languages, and it's also not even kind of true for English. So for example, numbers are numbers words. Is 1, 2, 3 a word, or is 1, 2, 3 words? And do you want to have 50 different tokens for all the possible different numbers you could possibly have? That's a choice. The next one is in other languages. So for example, right here we have, this is Japanese, this is photos of a temple. The space does not occur between all words in Japanese and in other languages. I think in Chinese, actually, there are no spaces between characters, unless, of course, you're putting in English midway between the two. And so because the spaces are important, but don't always occur between words, you want to actually model them. And now I have a cappuccino and life is better. And so we're going to actually add in meta space tokens, which you can see here as these underscores. So we can actually learn where do we put spaces in the language we're trying to model. And then finally, as you saw earlier today, there's no words there. That's just a bunch of molecules or a bunch of atoms. So where do we even split? And as I think we heard earlier, you can use a really nice regex, and we can basically split atom-wise into that nice, wonderful sequence. Okay, so in our particular case, what we're going to do is we are going to split on punctuation. So if we saw, so to take ourselves back to the don't example, we're going to split that as DON, then apostrophe, and then T, which is kind of weird as a tokenization. And this is what we get. So we can see that we have basically separated all of our words out, which looks really nice. Of course, we now have this weird thing where we have a data, apostrophe, and S. Those are 3 different words. Should apostrophe and S kind of be merged into one? Probably, like in terms of linguistics. Hopefully the model is going to basically learn to combine those. Or if we're doing subwords, and actually kind of a point on this, you might think, okay, well, this doesn't really matter because I'm just going to use BPE or Unicode or whatever, and they're going to do a merge. The problem is merges within these models typically are subword, and so there will never be a merge between apostrophe and S. And so it won't be able to recover this decision that we've made right here. Okay. So now that we have this wonderful sequence of words, we now need to make it a sequence of integers. And because we're going to start with the simple things, we're just going to do word level encoding. We could also do character level encoding, but that's neither here nor there. And realistically, if you want to do a multilingual model and use Unicode, you would need a vocab that is very large. I think it's 146,000 characters, or that, or like 400,000. Okay, so what is word level tokenization? We're going to look at our corpus. We're going to identify all of our unique words, and then we're going to assign a unique identifier to each of them. And then lastly, when we're actually at inference, if we find a word that we don't know, we're just going to mark it as unknown. We're going to call it a day. Now, this originally kind of came out of the area of natural language neural machine translation, in which case unknowns you can kind of get away with because if, for example, you don't know my name, you can maybe just copy it over and it doesn't really matter. If you're talking, say, chemistry, and you don't necessarily know what the atom is, you might not be able to make a good prediction at all. And so in some cases, it's really important that you can tokenize every single word. And in other cases, you might be able to fall back on something that's sane or at least reasonable. The other flip side here is depending on what your task is. If you're trying to embed a sentence, it probably doesn't really matter whether your name is Bob or Sally. And arguably, there should be no difference. But a lot of these models, there is. We don't want that. Okay, so how do we do this in Hugging Face? It's really simple. What we're actually going to do is we're going to catch up to myself. When we did one before. So hopefully while I'm talking, it's going to catch up. But all we have to do is import our model that we want to train. We have to import a trainer. And then we have to tell it what we're going to tokenize. So we're going to say, hey, we're going to do a word level. We're going to do an unknown tokenizer. There's a couple of additional options here, namely our vocab size. And well, not really our vocab size, just a vocab. And then we can provide our normalizer and pre-tokenizer that we set up above. Then we're going to set up our trainer. And we're going to just run this, which I think should just go. Where am I at? All right. Now it's running. And I think it takes a couple of seconds. 13 seconds to be precise. So again, pretty fast. That was a very large, well, it's about a couple 100 megabytes of data, but or tens of megabytes. Okay, so now what we're going to do is we're going to look at what that looks like. How did it actually do its tokenization? This is a little function that basically just does the tokenization, prints out what happened. Have fun with it if you want to, but you know, you could also just not. So we hit run. And now we're going to go demo that tokenizer. And so what we can see is that, not surprisingly, it tokenizes on each word. That's why we get those alternating grade things. And it doesn't know certain words. So it doesn't know what unveil is. It doesn't know gleam. Surprisingly, it doesn't know decode or crisp. And this is, of course, the downside of a word level tokenizer. If it doesn't show up in your dictionary, in your corpus, you're never going to learn it. The flip side is you can have a pretty small vocab. And so it can be a lot cheaper to train, can be a lot easier to train. And now, of course, the last thing we can do is we can do some post-processing. So we can, you know, pretend we're doing a BERT level model. We can throw a separator, a class in there, and we can put that in. We can find out where do the foundation models go. Okay. Any questions up to this point? Okay. So you're going to hear a lot more about byte pair encoding in a bit. And so I'm just going to kind of give you like a high level summary, which is essentially you're going to take your corpus, you're going to find your words. You're then going to count the frequency of co-occurring characters within each word. And then you're going to potentially merge the most frequent one, most frequent pair. And you're going to keep repeating that until you have a vocab that you like. That didn't make a ton of sense. Don't worry, we have a whole section dedicated just to this model. But what we can now do is we can, again, do the exact same thing as we did before, but this time we're going to use a BPE trainer and a BPE model. And once again, it's going to take not particularly long, 10 seconds, 3 seconds faster. And we can see here, whereas before we weren't able to tokenize Gleam or Unveil, or let's check out that decode. We could not check out and do the code, but now it works, right? And interestingly, we're kind of making a sane tokenization, right? We have code and D, which is at least more consistent with the underlying grammar. No, that's what do we go with, Crisp? Oh, yeah. That's a weird one. It's also kind of surprising. We get some odd ones that are quite long, like algorithms got its own token. Which is like, it is Wikipedia, so they're probably talking a lot about algorithms, but a bit unusual. And interesting enough, so again, cool point here is we're using the exact same vocab size. It's 3,000 tokens, 30,000 tokens, but now we've eliminated essentially all of our unknowns. So we've gotten a little bit better. Okay, so that's BPE. The next thing you could do is word piece. So funnily enough, if you go to Hugging Face and you train a word piece model, you're basically actually just training a BPE model. And the reason for that is that Google has never released what the heck a word piece model is, or at least they haven't released the code. They have described the algorithm. And so to give you kind of like a high level summary, the point is that instead in BPE, you're going to be merging pairs that occur the most frequently. In word piece, ideally, you're going to be identifying merges that have the largest expected information gain. So you're going to be looking at the relative frequency of both characters separately as well as together. And if it's worth it, it will make the merge. In terms of how this thing is actually being trained, it's literally a BPE. That's how the merges are going. However, at inference time, it's different. So a BPE tokenizer, you first tokenize based upon your alphabet, and then you apply merges sequentially. In word piece, there is no merge list. You just have a full set of tokens. So that includes both your base alphabet plus the merges. And you're going to sequentially, you're going to look at your word, you're going to find the biggest token that you could possibly apply, and then you're going to apply it, and then you're going to keep doing that until you tokenize the entire word. If you find that you've tokenized, say 20% of a word, and then those last couple characters you can't tokenize because you don't have a token in it, the entire word gets marked as unknown, as opposed to in, say, BPE, where just that little section of the word would be unknown. So that, again, trade-offs. And once again, if we want to train it, we do the exact same thing. We import our model, we import a trainer. We're going to do the same thing where we're going to tell it about our vocab size. We're going to give it an unknown token, which is unknown. And then we're going to train it. And this one, look at that, 5 seconds. It's getting faster. And let's see how it did on Crisp this time. Oh, nope, same thing. But also, interestingly enough, you can see dec. The code is now dec and ode, right? Which makes sense. A dec probably shows up relatively frequently. You have decibels and decade and other things of that nature. But now, instead of having a D and then a code, we're doing that bigger segment. Okay. Now, we're going to do unigram. So unigram is interesting, mostly because it's kind of a language model unto itself. And it's different from the previous three in that there is not a unique tokenization in the model. So whereas BPE and word level and word piece are going to come up with a singular tokenization for a given word, unigram is going to essentially compute all the possible tokenizations based on its set of tokens, and then compute a probability of that particular scheme for each word. And then it's going to use, at test time, you can either draw the most probable tokenization, or you could sample from, say, the top 100 possible tokenizations. What does this mean kind of practically? So you can imagine right now we have like a grade choice. So choice you could tokenize as CHOICE, right? Or you could maybe have a single token for choice. And that's important because your language model at the end of the day, right, is going to be predicting the next token in a sequence. So your segmentation does matter. And this effectively allows you to marginalize out your choice of segmentation. The problem is, in order to do this, you need to train a model with a very large vocabulary, i.e. use BPE. And then you're going to start sequentially removing tokens until you hit your target smaller vocab size. How do you find out which token to remove? Well, you compute the log probability of removing that token, and then you drop, say, 10, you sort it based upon how relevant each of those tokens are, and then you drop, say, the top 10%, and you keep doing that repeatedly. So whereas the other models, you basically train a tokenizer once, this thing, you have to train multiple times this tokenizer, and every single iteration, you're going to be making it a little bit smaller, one at a time. And while realistically Hugging Face again doesn't implement this, you could then draw samples from all the possible tokenizations. Okay. And as you probably have gotten quite used to now, training this thing is very simple. We're going to import our tokenizer. We're going to tell it about our thing, and we're going to then train it. Interestingly enough, we had the shrinking factor. This is new. And this is telling it how much are we going to reduce our vocab by every time. So we're going to start with a tokenization. I think I'm not actually sure what the initial vocab is, but let's say it's 100,000. You're going to remove 10,000 tokens, so the least relevant 10,000 tokens, and then you do that again. And then eventually we're going to end up with our total target here, which we're going to do about half the size of the word level encoding, so 15,000. And see where that gets us. So let's go look at that. And how do we do with our crisps? Still likes that beef. But decode is now even weirder, right? We have a D, an E, and a code. But again, you can also see that we're not really seeing a lot of unknown tokens. And we've also managed to essentially the size of our vocabulary. Okay. Questions so far?
Keep going.
So, of course, training a tokenizer can be a bit of a pain. You can make a lot of choices. Maybe it's just not relevant for what you want to do. You just have a bunch of molecules, or you just have a bunch of text, and you want to tokenize it and be off to your races. Lucky for you, there's a whole host of pre-trained models out there. So we are going to look at the GPT-2. Unfortunately, they don't release their later ones, but Llama does. You just need to sign a thing, and I didn't want to do that for this particular thing. So we can grab GPT-2. We can see how it tokenizes. Let's see what it does with that crisp. It knows how to tokenize crisp. Good for GPT-2. The other thing that's kind of weird here, though, is we can look at our tokens, and we can start seeing that for some reason we have this G apostrophe being put in before this. And this essentially comes down to the normalization. So GPT-2 actually models Unicode, and so they are essentially marking these words as non-Unicode. If you're not looking for, maybe your generic thing, we have Galactica. Spells a different blank set of tokenizers. We can see again, it does have Unicode normalization going on in there. Or maybe you're interested in figuring out what you should be doing this summer and want to learn about foundation models. So how would you do that? Well, you go ask it basically a RAG system. You give it the question, how can I learn more about scientific foundation models? And of course, the answer is 10 SciML summer school. And so we want to be able to pair that query. And so there are tokenizers that are designed for that. In this case, this is BERT. Or you have molecules. IBM has released their mole former tokenizer. And so we can see how this, which I believe is serotonin, the thing that promotes focus, get when you sleep. We don't know what that is. And we can see how that gets tokenized. So as expected, we're basically splitting every single atom into its own separate unit. Or if you want to do it with selfies, there's a selfie former pre-trained tokenizer that's out there. And here we can see that it is essentially splitting. It's first eliminating all these brackets because they're effectively redundant in the selfies language. And then tokenizing them all separately. Right. So that's what you can do if you don't want to build your own. But now, of course, the big question is, which one should I use? And it's not necessarily it's not really much in the way of like actually assessing the relative merits of one tokenizer versus the other. Most of the literature is focused on, okay, I propose a new tokenizer, let me now go train a foundation model and then look at how my loss is the best, which there's a lot of steps in there, and maybe it's your model's better, maybe your data better, maybe your tokenizer is better. Nobody tells you how they train their foundation model, or at least the big open AIs of the world. So it's a little bit hard to do an apples to apples comparison. But one thing we can do is we can measure something called fertility. So fertility is how many tokens does it take me to represent a word on average. So it's if I need a lot more tokens, I have a higher fertility. It also means that it's more expensive, right? Because if I had to, the cost of evaluating any given sequence is proportional to the length of that sequence. So if I have very, very short tokens, I'm going to have an effectively very long sequence fed into my transformer, and then I'm going to spend more money training it at inference time, the whole 9 yards. The flip side to that is maybe I have a really long sequence because I have a very small vocab that's, say, almost character-based. Well, in that case, now I'm not spending as much on my encoder layer in terms of number of parameters. So maybe there's a bit of a trade-off there. But either way, we're going to go look at them. And particularly, we're going to be evaluating their fertility on their validation data sets for the wiki text. I have commented out the former and self-former tokenizers for this assessment, because as you may have noticed, self-former only knows about the words branch and ring, and I think Wikipedia has a bit more in its vocabulary. Of course, it's summer school, so YOLO, have a field day, uncomment, run, but like it's not going to do well, and it's not really supposed to. I will say it does surprisingly better than you would think. Okay, so computing this is pretty easy. You're basically just measuring the length of the encoding. And we can do that for all of our various tokenizers. We can see that overall, they're pretty similar. We see a big spike all the way over to the left. So most of the time, we're going to be able to have a really short sequence. So it's going to take us most words. If you're doing a word level thing, it's going to be about 9 tokens, which is of course not really true because it's really, it basically means that most words are 9 characters long because we only use 1 token per word. Whereas if we now switch over to BPE, we see an increase of 1. So that's kind of great because it essentially means that we have the same vocab size, right? We're going to see a slight increase in fertility, but we've effectively eliminated the risk of running into something that we don't know about because now we don't have a dictionary that we have to look up our words in. We can just split them up into small pieces. We also can see we have these really long tails where sometimes we're using a lot of tokens to represent the words. And that's because some long words are really long. If you look at German, they like to basically make these massive compound words, and that results in this. So instead of doing just a raw fertility score, let's look at the number of tokens required per character. So the number of code points specifically, because again, this is Unicode and Unicode is weird. And so what we can find is that essentially there's a shift as you go from like, they're all kind of the same, but there is some like notable differences. So we can see there's a nice peak around here at 4, but there is this kind of trough for a couple of them. I think it's the bigger ones. So for example, I believe this is BERT. This might be GPT-2. Is really good with some of these. It's able to get kind of a nice little hump here. So it's able to use, well, in this case, it's essentially requiring, it's only able to represent 2 code points per token, whereas everyone else kind of is pushed more towards larger sequences. So yeah. Okay, and then of course the final question here is what percentage of the words are actually going to be tokenized and what are being marked as unknown. And what we can find out is that turns out we're not very good at trained tokenizers. All of ours are non-zero. But you can also see that going from word level to BPE is a really big deal, right? You're going from 45% of the words that you encountered, you had no idea what they were, to less than 1%. You could imagine throwing out essentially every other word I said might not make that big of a deal in your comprehension, but maybe other texts it does. Interestingly enough, of course, is that the GPT-2 and the Galactica models are doing pretty fantastic in essentially tokenizing everything perfectly, which isn't perhaps super surprising as they are trained on this data set. But there we are. Okay, so if you love this and you'd like to learn more about these things, there's a whole list of additional resources from Hugging Phases documentation to some fun papers about these actual tokenization methods and the history of tokenization, all of that good fun stuff. Any questions? But that is all I have. Great. I believe we're now going to be switching over to Alex Brace to be talking about BPE. So you'll get to learn a lot more about that. Yeah. Thank you very much for your attention.